Our last talk of the afternoon is Perdikaris, who is from University of Pennsylvania, and he's been there just about a year now. So he's been doing quite a bit of work on using neural networks. So we come back to almost the first plenary talk around thinking about PDEs, neural networks for PDEs, and so Paris has really nice results along this direction. Paris.
Thank you very much, Nathan and Steve, for the invitation. Actually, it's been a really fun day so far. I think the talks we've seen are setting the foundations for a new type of maybe neural scientific computing. And to this end, I'll share some of our results on this topic. So I guess the title has two components. One is physics-aware deep learning, which is essentially how can we take prior knowledge, physical and first principles, and try to embed them in deep learning algorithms, and then try to use those algorithms to model deterministic and stochastic systems governed by partial differential equations. So let me start with a big overview of why using neural nets in this context is an exciting idea. And that is related to their flexibility in allowing us to develop predictive tools that span a wide range of applications. Because in reality, we never have perfect models and we never have perfect data. And essentially, we want to have a predictive framework that allows us to seamlessly interpolate between the data-driven world and the model-driven world, just because the applications actually dictate this. So on the left, for instance, you have an application where little modeling knowledge is available. So that's a self-driving car. We don't really have a model for describing the behavior of fellow drivers or pedestrians, but we have massive amounts of streaming data, either coming from positioning or camera data or LiDAR data and so forth. And essentially, this is the data-driven regime where things like neural nets or machine learning techniques are thriving these days. But then you can do it to the other extreme, and here's, the movie is not playing here. It's supposed to be a movie of a CFD simulation parts an aircraft, in which there's a lot of modeling knowledge. You know conservation laws, you know how to mathematically describe the evolution of this phenomenon. Then you can translate those laws into computer algorithms and use supercomputing resources to simulate the system. But that's a very expensive process. You cannot really afford to do that endlessly. So the cost of data acquisition is very high. Therefore, maybe a simple realization of this problem gives you a very high dimensional data set, values of the velocity field and the pressure at every grid point. That's essentially a single data point in your data set, right? A single very high dimensional data point. So now the goal is to come up with predictive models or surrogate models for analyzing and optimizing such systems. And in this endeavor, we have to face a series of challenges. One has to do, especially in physics-based applications, one has to do with the high cost of data acquisition. Let that be a supercomputing simulation that would have to run to simulate the real system in high fidelity, or an expensive experiment. Then, associated with that is that we have limited and high dimensional data. The data could come in multiple modalities, such as images or time series or scattered measurements. It could be corrupted by noise, there could be missing data and outliers. And then if we're thinking in the context of design or control, we have to deal with parametric choices. And then, of course, we have to say something about uncertainty quantification if we care about doing things in a robust manner. So the hypothesis is whether we can use tools for machine learning or deep learning to tackle some of those challenges. So today I'll try to quickly cover two developments. One would be what we call physics-informed neural networks, and essentially it's just a simple formalism for trying to encode or approximately encode prior information in neural networks. And then using this as a building block, we'll try to extend this work into modeling stochastic systems, in which essentially we're not really trying to approximate their function using a neural net, but we're trying to approximate the probability distribution over possible outcomes. So let's first start with what we refer to as physics-informed neural networks, and the disclaimer here is that this is a very old idea, very much so like most ideas in neural nets. To my knowledge, it goes all the way back to 1992, the work by Perdikaris and Unger, and then 1998. And essentially, these were very patient people because they said, okay, let me try to use a neural net as a representation for solving a partial differential equation. So not use Lagrange polynomials, or don't use finite elements or finite differences, but represent the solution of the PDE using a neural net. So here's a feed-forward, fully connected architecture that takes as input space and time coordinates, pushes them through some hidden layers, and here's an output. So this is a continuous representation of your solution as a function of space and time. And that is a differential representation. So I can take derivatives of this with respect to space coordinates or time coordinates. So essentially I can construct, I can apply any nonlinear differential operator on this representation. And the reason why these people were brilliant is because they had to do this manually. And they have to also derive the backpropagation from this manually. So what we do here is we take a leap of faith, and instead of doing things manually, we take advantage of modern software. So essentially, this representation creates a computational graph, which we can then differentiate with respect to input parameters or input controls, and then form the residual of a given partial differential equation. And that essentially will help us construct loss functions. We'll use those residuals to construct those physics-informed regularizations in our loss function that will help us to train those neural networks from actually very limited data. All right? So anytime you have questions, please feel free to interrupt. So this is sort of the general setup. We're given a differential equation in this form, which could maybe depend on some unknown parameter. We'll see some examples later. And then it's really simple. So we'll use a neural net to represent the unknown solution. That essentially defines a residual for this equation, because essentially the neural network initially is not trained, so this equation will not be satisfied. And we'll try to train this neural network using a composite loss function that has two objectives. Objective number one, fit any data we may have for the solution. Those could be initial or boundary conditions or measurements inside the domain. So by the way, this sort of framework is a little bit disrespectful to classical numerical analysis, because we don't really need to have boundary conditions or initial conditions. These could be just measurements that we have inside the domain. And then there's a second term that is trying to force this residual to be as small as possible. So this is the residual of the PDE. So that is what will encourage the neural network to produce approximations that approximately satisfy the PDE. And I'm using the word approximately because this will never be exactly zero. Right? Another aspect why these techniques are a little bit disrespectful to classical numerical analysis is that they can be implemented. You can write PDE solvers in 40 lines of code in Python or 20 lines of code in Python. So it's extremely simple. So essentially, you just define a neural network for your solution, and then you use automatic differentiation, for instance, in TensorFlow, simply by calling the gradients command and then form the residuals. Here's just an example for the Burgers equation in one dimension. All right, and then this is sort of a summary of how the method works. These are the training data, so they correspond to the initial condition of the Burgers equation. So randomly sampled at t equals 0, and then some boundary conditions that are scattered for all the x's and at some times. So these are the data that we're trying to fit. And then inside the domain, we have a set of collocation points that we can choose randomly or adaptively, depending on the problem. And these are the points in which we want to minimize the residual of the PDE. And if we do so, we can train a neural net and we can get predictions like this for this sort of deceptively simple problem.
What happens if you go outside the domain where you train?
So as long as you place collocation points outside of your domain while training, then the method is able to generalize outside of the domain. So it's the collocation points and the knowledge of the physics that allow extrapolation. So yeah, so I'm calling this a deceptively simple example because if you're trying to resolve the solution using a classical numerical method, you need to be very, very careful in how you will discretize the domain. So the viscosity for this, this Burgers equation at the implicit limit, we have very small viscosity, and the solution develops a steep internal layer around x equals 0 at finite time, which is typically very hard to resolve. Here, these results are of relatively good accuracy. The relative to error is about 20 million before, and the simulation takes about 60 seconds on a single Python GPU. All right, so this is just a demonstration of what the method can do in the context of forward problems or solving PDEs. So this is the context in which you have a lot of modeling knowledge, you know exactly the governing equation, and you have a little bit of data, initial and boundary conditions. But I would not really advocate that this is a great method to use for replacing your classical solvers. Okay, this is just a proof of concept that the method, the technique works in this setting. What is more interesting to me is sort of tackling inverse problems, and here's another example, again, on the canonical setting, in which now we may not know exactly the governing law, and we can take an approach like a Cindy type approach and construct a dictionary of terms that could parameterize our governing law, and then the question becomes of identifying the coefficients. But on top of that, we can infer quantities that we could not measure or we didn't have measurements of. So here's an example of a canonical flow. Again, we saw that earlier, 2D flow past a cylinder. So this is a periodic steady state. We have this Kalman vortex state developing. And now let's assume that we have data out of the system in space and time of the two velocity components in this box behind the cylinder. So this is a cloud of scattered points in space and time for the u and v velocity components. So now we can construct a neural net that takes space and time as input, predicts u, v, and pressure as output. Based on that, we can construct those physics-informed residuals that will guide our loss function for training the neural net. And then once we train the neural net, we can recover the terms that contribute to actually what looks like the Navier-Stokes equation. And on top of that, we can predict the pressure for which we didn't have any data to train the model. And if you notice carefully, the prediction for the pressure is qualitatively correct. So the predicted versus the exact, there's a different scale, and that is because the pressure in Navier-Stokes, we only have the pressure gradient, so the pressure is only identifiable at the constant. But if you subtract the mean out of those two predictions, you get a very good agreement. So moving now beyond just estimating parameters, which was just this case, we were trying to estimate the constant, essentially the Reynolds number and the constant behind the advection term, you can extend these techniques to even try to estimate fields or constitutive laws. So for instance, here's a simple example again on a linear diffusion equation with this unknown diffusivity that depends on the actual solution. Now we can use a neural net to represent again the solution u, but we can use another neural net to represent this mapping k of u. Now in this setting, we have some data for u, some measurements inside the domain, but we don't have any measurements for k. And we can use exactly the same techniques to come up with a loss function and try to infer this nonlinear diffusivity out of the measurements we have. So this is just to show that the method can be extended to handle variable coefficients or continuous flow. A more interesting extension going beyond prototype academic problems is in the context of simulating blood flow in arterial networks. So that partially comes because I have a really big medical school next to my office. So it's easy for that to do some interesting collaborations. So in this setting, what we want to do is to try to use neural nets to model cardiovascular mechanics with the goal of monitoring hypertensive disorders. And then the catch there is that we cannot really, in this context, we cannot measure the quantities we're interested in a non-invasive manner. So for instance, if we want to measure blood pressure, we need to perform surgery instead of catheter. So it's really hard to infer the quantities we're interested in. So now we can set up this physics from neural networks to simulate blood flow in arterial networks. That's essentially a system of hyperbolic PDEs in a network. And then starting from measurements that we can obtain in a non-invasive manner, such as wall displacement measurements and blood flow velocity, we'll try to infer the pressure or other quantities that we're interested in, such as stresses and so forth. So again, we have this composite loss function that on one hand is trying to fit and encourage the neural nets to fit the measurements for wall displacement and velocity. On the other hand, it's trying to minimize the residual such that these conservation laws are satisfied. And then there's another loss part of the loss, because now we're solving PDEs in our network. We need to propagate information across the interfaces, so we need to ensure conservation across those interfaces. So here's just an overview. We start from MRI data obtained in the clinic. So you see some cross sections here that measure blood velocity, and we can also extract the arterial wall displacements. And these are some predictions of the model in some validation data. You see the predictions are not perfect, and that is because those data is heavily corrupted by noise, but it gives you something that is in the ballpark and is reasonable. It gives practical and meaningful information to the clinicians. All right, so I sort of took the opposite approach, showing you how you can use those methods for PDEs, and now I'm going to talk about ODEs. Some extensions of these techniques can be used for systems identification in ODEs. So now we are in the purely data-driven regime, where you have time series measurements out of a dynamical system, and your goal is to infer the right-hand side. So here we're going to take a non-interpretable approach, as opposed to what we saw earlier. So we'll try to estimate this black box function, and we'll do so by employing classical temporal discretization schemes. So you can discretize this ODE, you can pick your favorite time integrator. That will give you a physics-informed loss function. Then you can just minimize this loss function and train a neural net for identifying F. So here's some example results for the Lorentz system. But what I want to allude to is that we can take those ideas and push them to the other extreme, where we have no data whatsoever. So if that was a case where you have data and you want to infer the dynamics, here's another example for the Lorentz case, where now let's say we know the dynamics, we assume that we know the dynamics, and we want to come up with a technique that learns essentially an integrator for the system. It learns how to construct the flow map. So our goal is for any given initial condition of the system, we want to be able to predict trajectories without really using conventional simulators. All right? So the way you can do that is, okay, G here is the dynamics and it's known. We can construct a neural net approximation to the flow map by invoking the classical Runge-Kutta time discretization schemes. This will give us some residuals for training the neural net. And essentially what happens here, we have a mechanism for training the neural net. We'll try to achieve two goals. One, we'll try to construct trajectories that satisfy the dynamics. And two, we'll try to construct trajectories that start from the initial point we specified. So essentially, we're training the neural net by sampling initial conditions from some distribution, let's call it P-train, and that neural net tries to figure out how to generate trajectories out of those initial conditions that satisfy the dynamics. But now the interesting part is once that neural net is trained, it can generalize to initial conditions that are far from what we've seen so far. So we can now, this blue distribution cloud has zero almost overlap with the initial conditions we have used for training the network, and we can still generalize very well. So this is a purely extrapolative task that you can achieve by using the self-supervised, and I'm calling it self-supervised because there's no simulated trajectories used in training the data. The only thing that is used is knowledge of the dynamics. All right? Okay, so that was the first part of the talk, and now I'm going to move on to extending this for modeling stochastic systems. So if you have any questions on this part, maybe that's the time. Yes?
Do you use any regularizations for this loss problem?
No, that was a very simple, no, there was no additional regularization. So this is essentially the loss function that we're using. So it's trying to minimize those residuals that come from the Runge-Kutta discretizations of the dynamic system. And I should mention that it doesn't matter what choice you make for this Runge-Kutta discretization. For instance, we can use an implicit Runge-Kutta method with 100 stages and sort of infer all the nice properties like A-stability and the very low truncation error of those methods. So that allows actually to take fairly large time steps and perform predictions in a long time horizon. Any other questions?
Is there anything about this neural net approach that gives you, say, better ability to extrapolate than you would see with a more traditional library-based or other approach?
What other approach? Sorry?
Library-based approach?
Well, the library-based approach would learn the dynamics for you, I guess, and then we can use a conventional simulator to go ahead and simulate the trajectories. So what happens here, we're essentially learning the integrator. We're essentially learning what the Runge-Kutta method does. I mean, very much so, like a couple of talks ago, we saw a method of learning how to compute fluxes or derivatives of a simulator. Here we're learning the time integrator. So the benefits is, okay, if you know the dynamics, why don't you go ahead and use a classical simulator? Well, I guess the benefits here is that once you know this neural net, then you can rapidly generate trajectories. You can save the computational time, so it's just forward pass out of the neural net, and you can generate massive amounts of trajectories very fast. Yeah.
So I want to make sure I understand. You start with the dynamics and you're learning the integrator weights.
You're learning a neural net that learns how to map a state at time xn to the intermediate Runge-Kutta stages and the state at time xn plus 1. So you're learning the infinitesimal flow map of the system.
And in the previous example, how did the system ID problem work there?
In the previous
Just
example?
on the slide before.
So here I don't really show. So essentially, here you have data, you have time series data, so you know what xn and x minus 1 are. So that gives you a residual, and thus you're training the weights of the parameters of this neural net.
And what are you identifying?
The weights and the biases for the neural net representing the dynamics. So in this,
So you don't get the system back that you've written, but you get Integrator.
And then it's okay.
You learn the right-hand side as a black box. Here. So this is the, in this setting, you don't know what the dynamics are, you have time series measurements, and you're trying to learn a black box model.
But the black box is a neural net.
Yes, a black box is
I'm-
And then this is the other extreme that you know the dynamics, and then you want to learn how to generate trajectories or learn the flow map of the system. Okay, all right, so let's move on to the next setting, which is the modeling stochastic systems. So in this case, we will deal with systems that produce random outputs, and this randomness could come from different sources. So maybe our outputs are corrupted by noise in our observation model, or maybe there's inherent stochasticity in the dynamics, or maybe there's some parametric uncertainty that our solution depends on. So it doesn't really matter which of those cases is the truth in this case. What matters is that we have some dynamical system, perhaps again it depends on space and time, maybe described by partial differential equation, and now we have a random output. So we care about characterizing this probability density of what is my solution given a point in space and time. And there is, that alludes to an entire field of uncertainty quantification. There's many different methods of trying to approach this and try to characterize the statistics of the output. Mainly, those approaches are based on quadrature techniques that try to approximate, let's say, the expected value of U or the variance. And those work fairly well if the sources of stochasticity are relatively low dimensional, but they have, the phase the issue of Kersel dimensionality when the stochasticity is higher dimensional. And they require the repeated evaluation of simulators. So in a Monte Carlo fashion or in a non-intrusive fashion. So here we'll take a somewhat different approach and try to use tools from probabilistic deep learning to try to directly approximate this conditional distribution. And our liberating assumption here is that whatever sources generate the stochasticity can be summarized by a set of latent variables, let's call them Z. All right? So whatever, let this be a high dimensional stochastic problem or not, the assumption is that there's some underlying hidden structure, some set of latent variables that can summarize this randomness. So essentially, we'll try to take models like generative adversarial nets or variational encoders to construct conditional probability models, what I call here physics-informed deep generative models that try to approximate this conditional probability distribution, with the catch that now this U will try to constrain it to satisfy the governing law. So models like GANs or VAEs allow you to construct marginal sort of conditional distributions of this form. Now we extend those to make sure that whatever samples are generated by this generative model will approximately satisfy the dynamics. So this is sort of like an overview of how you can construct conditional generative models. And the main assumption is that every observation, and that's just a sketch, a notional sketch of how the process looks like. So every output, and in this case our outputs could be continuous functions, not just points in 1 and 2D. Every output is generated by some nonlinear generator, let's call it a theta, and that will be a neural net, that takes as inputs space, time, and those latent variables that are random, and they're sampled from some prior. So essentially every observation in the physical space is generated by a point in the latent space, pushed through this generative mapping. And that induces a conditional probability model over the predicted solutions. So now we want to take this conditional probability model and constrain it to the underlying dynamics. So to do so, we have to sort of optimize some probabilistic objective, and that will be, in this case, minimizing the reverse KL divergence of the joint distribution of the generative models versus the joint distribution of the observed data. So we have now some data observations. And there's 3 ingredients for doing so. It's not a trivial problem. So one is how we can approximate KL divergences in general. And then second is how we can actually minimize them. And then the third one is how to encode those constraints. So I'll just quickly skim through the process. So it turns out that the machine learning community has developed some very flexible tools for approximating density ratios directly from samples out of 2 distributions, and this is scalable to high dimensions, based on the observations that any density ratio can be approximated by a binary classifier. So we can train a classifier that learns how to discriminate between samples from one distribution versus the other, and that gives us an approximation to the density ratio that then allows us to compute things like KL divergences, which are simply expectations over the logarithm of a density ratio. So that's intuitive number 1. Then ingredient number 2 is motivated by why we choose the reverse KL divergence as a training objective, and then has to do with the pathology of mode collapse in adversarial networks. So I won't have time to go into the details, but essentially the reverse KL divergence allow us to come up with a regularization mechanism based on the entropy of the generative model that help us mitigate this issue of mode collapse. So there's more details in the publications. So at the end of the day, we have an optimization objective which looks like a minimax game for training the discriminator, which is the proxy for approximating density ratios and KL divergences. And then, so the loss of the discriminator is a simple binary classification, so binary cross entropy loss. And then the loss of the generator is essentially the loss that is trying to minimize the KL divergence that's computed by the discriminator, plus this entropic regularization that helps to mitigate the issue of mode collapse. And on top of that, we have the PDE loss term trying to enforce the PDE residual in order to encourage the generative models to produce samples that satisfy the PDE. So here's an example of what these models can do for us. Again, a toy problem. This is a simple nonlinear ODE with random boundary conditions. So essentially, we know the exact solution for this problem, and then we assume that the boundary conditions are sampled from normal distribution. Here's a deterministic case where the noise of the distribution is 0. So, and this is the prediction of the algorithm. And then assuming you do have some uncertainty that is more related to the epistemic uncertainty of the neural net predictions. And then this is the case where you do have stochasticity in the boundaries. And what you see here, the x's are the actual training data. These are the only training data. We just have realizations of the boundary condition. Alongside with the residual, the collocation points to minimize the residual of the PDE inside the domain. And that is the prediction of the generative model that captures the mean, and you can also see the 2 standard deviations. And there's more systematic studies to assess the effectiveness of this generative model of approximating the statistics of the solution. So in this systematic study, we're trying to investigate the effect of the entropy regularization and the PDE regularization parameter, and we show how if you choose an entropy regularization equal to 1, then our model is essentially a generative adversarial network that suffers from the issue of mode collapse. Whereas if you add the entropy regularizer, you get a much more stable solution. So that was just a toy problem. Here's a slightly more challenging problem in which we're trying to evolve the Berger's equation from a random initial condition. So that's essentially an infinite dimensional uncertainty propagation problem, where the initial condition is sampled from a non-Gaussian distribution that gives you a lot of noise close to x equals 0, that is the location where the steep layer develops. And then the method can actually recover sensible uncertainty estimates to quantify aleatoric uncertainty in this sense. So what you see here is just predictions of the mean out of the generative model and the variance produced by the generative model, showing that the uncertainty concentrates around the location of the shock. All right, so I think I'm running out of time, so I'll just summarize, and I'll do so by thanking my student for doing most of the work, the sponsors, of course, again, the organizers for the invite, and you can access most of the details behind these works in these publications, and all the code is on the GitHub if you want to experiment with it. So, thank you.
Floor is open. Questions? Everyone's beat down.
Can you talk a bit about convergence issues in the optimization?
Which part? That's a very yeah. So
The first part.
Well, the first part. So yeah. So the first part comes with. It's easy to break. It's easy to break this tool.
I've broken many times.
Yeah. So to my experience, the tool is prone to breaking if you're trying to approximate a solution that has multi-scale features, or anisotropy, or chaotic behavior. And to this extent, I'm not convinced yet that this is a limitation of the method, but I think it rather exposes our limited understanding of properly setting up the problem, meaning properly scaling the equation, because the neural net expects things to be zero mean unit variance, properly initializing the neural nets. So I think there's a lot of things that we don't know about setting up the problem. That being said, A follow-up work that we've done is utilizing convolutional architectures instead of fully connected. These won't give you a continuous representation of your solution, so essentially you have to discretize and treat things as enigmas. So then you can compute derivatives using finite differences or Sobel filters instead of automatic differentiation. And these seem to be a lot more robust in simulating more complex problems, like, here's the Kormolov-Shapczynski equation or Berger's equation into the. So it seems.
Are you restricted to square domain?
Yeah, this is restricted to square domains, but could be generalized to complex geometries, either through the use of geometric deep learning techniques, or another approach would be not to throw away everything we know about scientific computing, use things like finite elements or spectral methods, but then try to use deep learning to accelerate the simulation process to complex geometry.
More questions? Okay, so before we leave, so we start tomorrow.